In our last lesson, we talked about how glycolysis uses up NAD+ and generates NADH in the cytoplasm. Glycolysis will give us our 2 ATP on net, but it also is going to give us 2 NADH. And normally we think of that NADH as a good thing because we can take it through the electron transport chain to generate ATP through oxidative phosphorylation. However, this relies on the presence of oxygen, and if we don't have oxygen, we can't do the electron transport chain. If we can't do the electron transport chain, we can't pump protons. If we can't pump protons, we can't create a gradient, and if we can't create a gradient, we can't make ATP. Therefore, if we don't have oxygen, we can't do that, but there are alternative routes to regenerate that NAD+ to keep the cycle going. It's really important that we regenerate this NAD+ to in order to have that reactant or cofactor for one of our reactions of glycolysis, this glycerol-3-phosphate dehydrogenase step, and also because NADH is going to directly inhibit our catabolic reactions. In our cells, in the absence of oxygen, what we typically do is we do this lactic acid fermentation, where we take pyruvate, we reduce it to form lactate, ship that lactate to the liver. The liver will then oxidize it back to pyruvate, convert it to glucose through gluconeogenesis, and we do this cycle again and again, the so-called Cori cycle, when this is happening from lactate generated in our muscles. Side note that the soreness, like delayed onset muscle soreness, isn't from that lactate buildup, rather from like small muscle tears and things like this. Although the lactate buildup can inhibit just kind of like your direct activity in the moment, it's not what's actually causing the soreness the next day. And that lactate is actually really important for helping your muscles get rid of the NADH, as well as to get more of the glucose that comes from the gluconeogenesis that was happening in your liver. So thank you, Cori cycle, for all that great energy, and don't keep blaming the lactate for all of that soreness. But anyway, that's not what we're going to talk about today. Today, we're going to talk about what happens if we do have the electron transport chain present and operational. So we have cells that have mitochondria, so we're not talking about like raw red blood cells, and we have oxygen so that the electron transport chain can actually function. In this case, however, we still have a problem because the NADH that we generate in the cytoplasm can't actually directly get into the mitochondria. And so we're going to need to use what we call shuttles in order to get equivalents of it in, because what we really care about isn't the NADH itself, but rather the electrons that it holds on to. When we talk about a shuttle, we're basically referring to a mechanism of transporting the equivalent of something into a different space where we can't just directly transport that thing. So we have to disguise it and kind of transport it in that way. And so hopefully it'll make a little more sense once I give you a couple of examples. The two main examples we're going to be talking about today are glycerol-3-phosphate shuttle and the malate-aspartate shuttle, which are ways in which our cells can take electrons from NADH in the cytoplasm, such as are generated from glycolysis, and transfer them into the mitochondrial matrix, where they can be used to power the electron transport chain. Let's start by talking about the glycerol-3-phosphate shuttle. So this over here. The glycerol-3-phosphate shuttle is going to take electrons from the NADH, and it's going to bring them in by passing them directly to Q from this glycerol-3-phosphate dehydrogenase. So remember that when we talked about the electron transport chain, we talked about the kind of mobile carrier Q. And that Q, that ubiquinone and ubiquinol, basically what's going to happen is that's that carrier that takes electrons from either complex 1 or complex 2 and passes them off to complex 3 in our electron transport chain. We also talked about how there could be multiple other routes to Q. And one of the routes to Q is going to be this glycerol-3-phosphate dehydrogenase. Mitochondrial one is going to be FAD, use this FAD and FADH2. What you see a cytoplasmic one is going to use NADH and NAD+. And so remember, those were going to be like mobile soluble carriers, whereas your FAD, that's going to be membrane embedded. And so the mitochondrial version of this is going to be embedded in the membrane, and the cytoplasmic one is going to be free floating, and they're going to be working together. In your cytoplasm, what's going to happen is you're going to take that NADH that you generated in glycolysis, and you're actually going to use it to reduce dihydroxyacetone phosphate to form glycerol-3-phosphate. So this dihydroxyacetone phosphate, this is what we had in our glycolysis. So this was this step here. And so normally we're taking dihydroxyacetone phosphate that we generated from this aldolase step, and we're using triose phosphate isomerase to isomerize it to glyceraldehyde-3-phosphate. That's not a redox reaction, it's just an isomerization. However, we could also take this dihydroxyacetone 3-phosphate and we could actually go and reduce it. And when we reduce it, then what we're able to do is we're able to generate glycerol-3-phosphate. When we generate glycerol-3-phosphate, now what we're able to do is we're actually able to take that glycerol-3-phosphate, which now holds on to those electrons. The glycerol-3-phosphate can now pass those electrons onto FAD in your mitochondrial membrane. And this is going to, then we oxidize it, so we reverse this reaction. But here we're passing those electrons from glycerol-3-phosphate onto FAD to form FADH2, which can then pass those electrons onto Q. So here we're taking the electrons from the glycolysis, passing them onto NAD, generating NADH. We then pass the electrons from NADH onto dihydroxyacetone phosphate, giving us glycerol-3-phosphate. We now take the glycerol-3-phosphate and we pass electrons from it onto FAD to give us FADH2. We pass those electrons from FADH2 onto Q to form QH2, which can then take things through the electron transport chain. So we're using these components that were generated in glycolysis, so this dihydroxyacetone phosphate and this NADH, and we're going to use them to sneak those electrons into the mitochondria. What we note about this is we're taking those electrons and we're passing them directly to Q. When we pass electrons to Q, well, here, if we bypass complex 1, we're not going to be pumping the protons that we would pump out at complex 1. Therefore, we're only going to get the yield of an FADH2, not the yield of an NAD+. This means that we're basically only going to get the equivalent of 1.5 ATP per our NADH that we were generating in the cytoplasm, instead of the 2.5 that we would get if we were to go and insert that complex 1 with our NADH. So there's less of a yield here than we would get if we generated that NADH in our mitochondrial matrix, where it could enter at complex 1. And we'll talk about a method in a second where you can actually still enter at complex 1, even if you generate that NADH in your cytoplasm. This is the main method that you're going to be, this glycerol-3-phosphate shuttle is the main route that you're going to take to get NADH equivalents to the electron transport chain in your brain and in your muscles. But in other tissues, they're going to use this route called the malate-aspartate shuttle. And this is where we go back to that idea of that malate dehydrogenase we were talking about before when we were discussing gluconeogenesis. So this malate-aspartate shuttle, we'll see what here is going to happen is that we take oxaloacetate, we take the electrons from NADH, we pass them on to oxaloacetate, reducing oxaloacetate to form malate. We then ship the malate into the mitochondria, where we have a mitochondrial malate dehydrogenase that can take the malate, oxidize it to make oxaloacetate, and the process use NAD+ in the mitochondrial matrix to generate NADH, and that NADH is now in your matrix where it can enter at complex 1, and therefore you're going to get the 2.5 ATP equivalents from NADH that enters this way. So it doesn't look so bad if you just look at it as a straight line. We're taking those electrons, passing them on to oxaloacetate to get malate, and taking the malate in. We can do this because we can't take the NADH in, but we can take the malate in. And so the malate is carrying those electrons into the mitochondria. I'm going to complicate things now to show you a more realistic view of what's going on. because unfortunately, there's a lot of kind of swappage that needs to happen in order for that malate to come in and in order for keeping this cycle to be going. In order to understand what's going on, we're going to need to review a couple of our concepts about membrane transport. Remember, we had that term where we transported two things through a single carrier. We call that co-transport. So we can have antiport, where things are traveling in opposite directions, or symport, where they're traveling in the same direction. Both of those would be forms of co-transport, and we could also have uniport, which is just going in this one thing at a time through. What we're going to see in our Malate-aspartate shuttle is we're going to see antiporters. So we're going to take one thing in exchange for taking something else out. This is going to allow us to keep a balance in our mitochondria and in our cytoplasm that's going to allow us to keep this cycle going. So the key thing to keep your eye on is going to be this electrons that are coming from this NADH. Those electrons, remember, are going on to oxaloacetate to give you malate. The malate is going to get shipped in, and then the malate is going to be converted back to oxaloacetate with the conversion of your NAD plus back to NADH. This is all you really need to do in order to get the electrons in, but in order to keep things going, you're going to need to regenerate oxaloacetate out in the cytoplasm. You might think, why don't we just ship that oxaloacetate back out? But there's no transporter for oxaloacetate through the mitochondrial matrix membranes. And so instead of shipping oxaloacetate out, we're going to have to disguise it and then transfer the disguised version out. We're going to disguise it in the form of aspartate, so that good old amino acid aspartate. How we're going to do this is using an amino transferase, in this case, aspartate aminotransferase, or AST. If you've heard about like your liver enzymes, and like AST is one of them, and basically aspartate aminotransferase is this really important enzyme, and it is used as one of the main transaminases, where basically you take an amino group from something and you pass it on to something else to give you something else. So we'll talk a lot more about this when we talk about amino acid metabolism. But basically, you can take any amino acid, remove its amino group, and pass it on to an alpha keto acid. So keto, it's got a ketone group, and it's in the alpha position to a carboxylic acid. That'll generate a different amino acid and a different alpha keto acid. We'll talk a lot more about this when we get into amino acid metabolism. But here what's happening is we're taking an amino group from glutamate and we're passing it on to oxaloacetate. This generates aspartate and leaves you with the remainder of alpha ketoglutarate. Aspartate can get passed through. Aspartate can get passed through in exchange for passing in a new glutamate. So you take out the aspartate and you take in the glutamate that you need to do this reaction again. In order to do this reaction again, you're also going to need to get rid of your alpha ketoglutarate, and you're going to need to take in more of your glutamate. So we took in the glutamate in exchange for the aspartate, where you take in the malate in exchange for taking out the alpha ketoglutarate. So we need to remove the alpha ketoglutarate in order to get rid of kind of our waste, and this will allow us to exchange it for malate. Our waste in the mitochondrial matrix, however, is not waste in the cytoplasm, because what's happening in the cytoplasm is basically we're doing the opposite of everything that we do in the matrix in the cytoplasm. So that aspartate that we shipped out, we can now take the amino group from that aspartate and we can pass it to alpha ketoglutarate. This alpha ketoglutarate is the alpha ketoglutarate that we passed out of the matrix in exchange for passing in the malate. So we shipped out the alpha ketoglutarate in exchange for taking in the malate. The alpha ketoglutarate that we shipped out now can accept the amino group from the aspartate we shipped out, remaking the glutamate. And this glutamate we can then ship back in. All of this was regenerating the oxaloacetate that we needed in order to then do this again to pass electrons onto oxaloacetate from our NADH to generate our malate that we can then ship into the matrix. So basically all this fancy dancy stuff is to regenerate the malate. So let's review one more time what's happening. Let's look at it in a different view in case this one makes a little more sense to you. What we have out here is we have our cytosolic mitochondrial dehydrogenase. It's going to take the electrons from NADH, and this is going to reduce oxaloacetate to form malate. So remember, reduction is gain of electrons, our good old oil rig. So we're reducing oxaloacetate by passing electrons to it. This generates malate. Malate can enter the mitochondrial matrix in exchange for the passing out of alpha-ketoglutarate. This is happening through the malate alpha-ketoglutarate antiporter. So it's an antiporter because it's transporting these things in different directions. You're taking the malate in, and now a mitochondrial version of malate dehydrogenase can then take that malate and it can oxidize it to oxaloacetate. So here's where the reversibility of reactions comes into play, because we're able to take this, the same like enzyme or different versions of the same enzyme and do the reaction in different directions in different compartments of the cell. Here we're going to be oxidizing malate to form oxaloacetate, and more importantly, to generate this NADH in the matrix. So we've taken the equivalent of an NADH out of the cytoplasm and regenerated it in the matrix. Now this NADH, because it's in the matrix, it's able to go directly into complex 1, and so we're going to get the full energy out of it. If we want to do this again, however, we're going to need to take this oxaloacetate and get it out. But we can't take the oxaloacetate out because there's no oxaloacetate transporter. Instead, what we're going to do is we're going to disguise the oxaloacetate. What we're going to do is we're basically going to take an amino group from the amino acid glutamate. And we're going to take that amino group and add it to oxaloacetate. This is going to give us the amino acid aspartate. And this is happening through this aspartate aminotransferase enzyme. That aspartate can now get shipped out. In order to get shipped out, it's going to go through this aspartate glutamate antiporter. As the name suggests, in antiporter, basically you're transporting two things in opposite directions, and it's telling us that we're transporting aspartate and glutamate. We're going to be transporting aspartate out and glutamate in. Glutamate, remember, is what we needed in order to get an amino group to pass on to oxaloacetate. This is going to allow us to generate aspartate. In the process of doing this, we're kind of left with the waste products from when we took an amino group off of glutamate. This waste product is our alpha-ketoglutarate. We can ship out the alpha-ketoglutarate in exchange for bringing in a new malate. So remember when we took the malate in, that was happening through the malate alpha-ketoglutarate antiporter. We shipped the alpha-ketoglutarate out, brought a malate in. And this is going to then allow us to get rid of our waste, bring in the new things we need. In order to make this a cycle so we can keep things going, we basically do the reverse of everything that we did in the cytoplasm in the matrix, everything we did in the matrix in the cytoplasm. So we can take this aspartate that we shipped out, as well as the alpha-ketoglutarate that we shipped out. We now take the amino group from that aspartate, pass it on to alpha-ketoglutarate. This is going to give us glutamate and oxaloacetate. The oxaloacetate is now ready to accept electrons from NADH. And that glutamate can now get shipped back in exchange for shipping a new aspartate out. So I know it seems really overwhelming when you look at a pathway like this, where there's a lot of complicated things going in. But the key takeaways are to think about what is the net effect. The net effect here is basically we're taking those electrons from NADH and we're bringing them into the mitochondrial matrix. Everything else is just to regenerate the system. The important thing is that we're the electron passing. Another important concept is that we can have reactions happening in opposite directions in different compartments or at different times. A final important thing is the idea of kind of shuttles, bringing in the equivalent of something when we can't bring in that thing directly itself. Also the idea of sort of antiport and introducing the idea of aminotransferases, which we'll talk a lot more about in the future, But this is going to come into play with amino acid metabolism, as well as when we think about the carboxylic acid cycle. Because remember, although we can break things up into cycles and pathways, it's the same sort of chemical logic happening. But that's going to be seen over and over again, which is why we did that glycolysis activity where we're really focusing on the chemical structures.